In one of the previous videos, I first clued you guys into a mysterious connection between complex numbers, a plus bi, a is the real part, b is the imaginary part, and these matrices of a very particular form, a, negative b, b, a. So whatever these matrices are, they better have the diagonal entries being the same and the off-diagonal entries being negative one another. So there's a name for matrices of this form. It's called GL1C, and I'll explain that notation a little bit later on in the video. But basically, it's the set of all matrices of the form a, negative b, b, and a, where a and b are real numbers. They're not complex, they're real. And they're not both 0. Right? If you had 0 plus 0i, a 0 complex number, I mean, that's just 0, right? That's the origin on the complex plane. That's both x and y coordinate 0. Then that would correspond to the 0 matrix. Otherwise, everything else will correspond to some matrix, other than the 0 matrix. So it turns out this is a group in the sense of group theory, in the sense of abstract algebra. There's also another interesting group you can consider. You can consider the set of all non-zero complex numbers. So as long as you're not multiplying anything by 0, this turns out to form a group too. So you should think about exactly what needs to be shown here. Multiplying these matrices together, or multiplying non-zero complex numbers, do you get another non-zero complex number or another matrix of this specific form where a and b aren't both 0? Can you find an inverse to each of these things, something you can multiply to get the identity? Here, the identity element is the identity matrix of the form 1, 0, 0, 1, which is of this form, right? The a's are 1 and the b's are 0. And the identity for C cross, this little C cross, the non-zero complex numbers, is just the number 1. 1 plus 0i. So the point is that these are both groups under multiplication. Here, matrix multiplication. Here, just the traditional multiplication of complex numbers. And so what we have really is a map which takes elements of C cross, so I guess I'm assuming a and b aren't both 0, and it produces for us an element of GL1C. So we get a map, phi, from C cross to GL1C. So I'm just calling this correspondence phi. That's it. And it turns out that this is actually a group isomorphism. So these things work out perfectly. So again, what does that mean? It means in particular it's a group homomorphism. It implies that phi of, I'll just write these complex numbers as z and w, those are both non-zero complex numbers, should equal phi of z times phi of w. Each one of these things is going to be a matrix. It's going to be a matrix of this form. You just take the real components and the imaginary components and put them in this form for z and for w. And then you multiply those two matrices, and you end up getting what you would have gotten if you had just multiplied them as complex numbers first of all, and then created this matrix. I'm not going to bother going through that computation because the first time I introduced this to you, I already went through that computation and showed you exactly how it works out. So you can go back and watch the end of that first video where I talked about this, and you'll see that what I really did prove is that this is in fact a group isomorphism, if you know what that means. And as an interesting tidbit, but an important one, the determinant of this matrix, if you think about it, it's a times a minus b times negative b. That the minus cancels with that negative, and it becomes a squared plus b squared, which is actually the norm or the modulus or the length squared of the complex number. And an important point for later on in the video, this quantity, this determinant, this modulus, is only going to be 0 if a and b are both 0. Well, that makes perfect sense, right? It has to be at the origin, otherwise this is going to give us the length. If we have any kind of non-zero aspect at all, then it's going to give us the positive length of that vector, of that element of the complex numbers. So only way that this is going to be 0 is if I just give you the 0 complex number. Or of course you can just obviously look at the algebraic expression a squared plus b squared. What's it going to take for these things to be 0? A and b are both real numbers, so that their squares are both positive, or 0 if they're both 0, and that's the only way it's gonna all come out to 0. So that's just an interesting little tidbit. But the point I want to make is that all of these guys, these matrices of this specific form, have a determinant which is usually non-zero. And because we've restricted our attention to the case where a and b aren't both 0, then we can guarantee that this is not going to be a zero determinant. So that's going to be important in a moment. But to really explain, the point of this mysterious connection, and it's so important, it's really the foundation of a lot of what we're going to be doing in complex analysis. If you understand things from a bird's eye view, this is really the whole spirit of complex analysis and what makes it so different from the real analysis. But in order to explain that, I have to do a little bit of linear algebra view. So, bear with me. First of all, remember that linear maps from Rn to Rn, so these are, remember, vector spaces. And if you learned about linear algebra in a nice abstract way, you'll remember that there were really two objects of interest. There's a field of scalars, and if you've seen abstract algebra before, you know what a field is. And in your first linear algebra classes, you were pretty much only interested in real scalars, real numbers as scalars. And then there was the vector space itself. And what was important, it's just some set V, but you would have something which takes in two elements of V, let's call it little v and little w, and it would give you a third element, and we just denote that by addition. It would be vector addition. I'll even denote with these little arrows on top what that looks like, elements of V. And then there was also a map which took in a real number, I'll call it little c, a scalar, and you would multiply it by your vector. Okay, so that's typically what happens in the abstract version of it, but you don't have to be abstract. There's also a theorem which basically says as long as everything's finite dimensional, you may as well be dealing with Rn. So I'm just going to talk about it as if we're just dealing with typical old Rn. So the point is that we have a way of multiplying by scalars. Rn can be thought of as the n by 1, n rows, 1 column matrices of just real numbers, just any old real number. You call it v1, v2, all the way down to vn. Those are just random real numbers. So it's the set of all such things. You add them component-wise, and a scalar multiplies by just multiplying each component. So just a quick review of that. Now, we're interested in particular maps from Rn to Rn, which are called linear. Okay, that means they obey two properties. That if you scalar multiply a vector by a scalar, and then you apply our map, it's the same as if you had applied our map to the vector originally, and then you multiply the scalar. So you scale first and then map over is the same as if you mapped over and then you scaled. And same thing here with addition. It respects addition too. If you add first and then map over, then that's the same as if you had mapped over first and then added. So these linear maps are things which really respect the vector space structure of Rn. So they're all of a very specific form. This is one of the chief points of linear algebra and what makes linear algebra so nice and so computational and crisp. They all come from multiplication by a matrix. Okay, and this is only applying to linear maps. If I just give you any old map from Rn to Rn, odds are it does not satisfy either one of these two properties. But how do we know if it obeys both of those two properties? Well, it has to be of a very, very specific form. It has to come from, what does f of v equal? It equals v, so here I'm writing v as a column vector, v times an n by n matrix that represents this function. So that's it. There's this correspondence between n by n matrices and linear maps. And the linear map is always given by taking a vector, thinking of it as a column vector, and then multiplying it by this n by n matrix. And it's important to keep in mind that since the domain and the range are the same, it's both Rn to Rn, this is always going to be an n by n matrix. Otherwise, the domain would be the number of columns and the range would be the number of rows. But it's both n in this case. So quick question. What if n is actually equal to 1? In other words, and this is a little bit weird, typically when we're thinking of vector spaces, you're thinking of these kind of arrows in higher dimensions, maybe 2 or 3 dimensions. But the real numbers themselves, let me draw it, just the real line here, with 0 there, actually R is itself a one-dimensional vector space over itself. So it's a little bit weird. If you ignore the fact that it's a field and you just look at it under addition and multiplication by non-zero scalars and so on, actually by any scalars, then it forms a one-dimensional vector space. So it's the field of scalars and it's the vector space in this context when n is equal to 1. But what do linear maps look like in that case? In that case, a linear map is a mapping f that takes R to itself, okay, and it's given by multiplication by a n by n, but n is 1, so that's a 1 by 1 matrix. Well, what does a 1 by 1 matrix look like? Okay, it has one term in it. You call it A or something like that. That's it. It's a 1 by 1. A 1 by 1 matrix of real numbers is basically just a real number. Okay, you may as well just put some brackets around it. That's it. So what's a 1 by 1 vector look like? Well, it just consists of one element right there. And when you multiply this out, what do you get? Row by column pairwise. There's no rows, there's no columns. It's 1 by 1. It just looks like AV1. Okay, so what's the moral of the story? In one dimension, linear maps are simply, quote unquote, multiplication by some number. Some number A is what I'm calling it in this case. Alright, and if you think about what the graph of such a thing would look like, so we don't typically graph linear maps because we're typically dealing with higher dimensions in linear algebra class, but because the dimension is so small, we actually can graph it in this case. Multiplication by some number, I mean, this is like the equation y equals ax. I mean, it's just a line of slope a. You know, it's a, there you go, slope a line. And that's it. So linear maps from R to itself, thinking of R as a one-dimensional vector space over itself, are very simple. They're just linear in the traditional sense. They're just lines, their graphs are lines in the traditional sense of the word from Algebra 1, and they pass through the origin, of course. There's no y-intercept. The y-intercept is 0. Okay, so let's keep going. Now, for these linear maps to be isomorphisms of vector spaces, so they're bijective and they're linear maps, then the matrix must be non-singular. And non-singular can easily be checked. I mean, there's a couple ways you could define it, but the easiest way to think of it is just the determinant is not equal to 0. Alright, so that should remind you, up here we had determinants of these guys that were non-zero. That's going to come up in an important way later on, but right away we can say, hey, these things are matrices. We can already think of them, they're 2 by 2 matrices, as mappings from R2 to R2 that are linear mappings. And they're not just linear mappings because the determinant is never 0 unless they're both 0, but we're ignoring 0 here. Then they're all going to be isomorphisms from the plane to itself. And I guess the moral is that these matrices of this very specific form aren't just any old isomorphisms, they're isomorphisms of a very specific kind. Remember, multiplication by complex numbers, and that's really what this amounts to, corresponds to a rotation by angle theta, where theta is the argument of the complex number. You know, so if you have a r e to the I theta, and that corresponds to a plus bi, which corresponds to this matrix, then you're just rotating counterclockwise by an angle of theta, and you're scaling by r. So again, I showed that in the previous video. I don't want to get too much into it. But I just want to point out that these things are isomorphisms because they all have non-zero determinants. And again, the question is, well, what does this amount to for 1 by 1 matrices? That's a 1 by 1 right there. Well, again, I mean, 1 by 1 matrix is simply of the form A. What's the determinant of such a thing? The determinant of a 1 by 1 matrix is just whatever that number is inside of it. So really what we're just saying is for 1 by 1 matrices, to have non-zero determinant means that the one entry in it, it only has one entry, is not 0. Okay, that's easy. So GL1R is what we call the set of 1 by 1 non-singular, so they have non-zero determinant, real matrices. Okay, or if you like, the whole point of it, like we just said, is it's the set of all isomorphisms from R to itself, where we're thinking of R as a one-dimensional vector space. As a one-dimensional vector space over which field of scalars? Over the reals. Over the reals. So remember, it's a vector space over itself. It is this field of scalars and it's the vector space of one dimension. So that's one nice way of thinking of GL1R. And, for what it's worth, as you might imagine, by replacing 1 by n here and n here, you'd get something which is also a group. GLNR. These things are groups, by the way. You multiply them, that's the same as if you had composed those isomorphisms. But I don't want to get too much into that. So GLNR also makes sense, but we're not so interested in that right now. Okay, but now here's the point. The complex numbers is a field too. So I didn't tell you what a field was, I just assumed you guys remembered it from abstract algebra. But a field is something which has, addition, it has multiplication, and the properties of these things are so nice that you can even divide by non-zero numbers. Divide by non-zero things. So it too is a field, and that means if you're thinking of vector spaces in the abstract sense, you can really consider vector spaces over the complex numbers. A lot of linear algebra goes through just fine if you replace the field of scalars R with any other field in the sense of abstract algebra, in particular with the complex numbers, C. So, really, everything does go through just as you would imagine. You can think of n tuples of complex numbers, n by 1 matrices of complex numbers, v1, v2, ... down to vn, where each of these things are now complex numbers instead of real numbers. So you can think of in tuples of complex numbers, and that forms something called Cn in the same way we had Rn, and it too is a vector space. This time around, though, the scalars are complex numbers. So I have a little note here. Don't hurt yourself trying to visualize this for n greater than 1. You can't. If n is greater than 1, C is already something two-dimensional. So if n was even just 2, you'd already be trying to visualize something four-dimensional, which is probably beyond what you can do. So you don't have to worry about visualizing it too much. Maybe focus more on the algebra than the traditional geometric way of viewing vectors as arrows. Okay, but the point is that this time the scalars are complex and everything pretty much works the same. Alright? You have a map F that takes Cn to itself. It's called linear, and now I'm stressing the fact that this is complex linear, if it obeys these properties right here. It respects vector addition, and that works in exactly the same way, and it respects scalar multiplication. C is still a scalar here, but remember now, our scalars are complex numbers, so you should be able to pull out a complex number. So just to be a little bit more explicit, let me draw a two-dimensional case for you. If you had 2 plus 3i as a scalar, times the 2 by 1 vector, this element of C2, I don't know what you want to call it. Let's say 3i, comma 4 minus I, or something like that. That should equal the same thing as if you first apply F to this column vector, and then you multiply by this scalar. So I'm just stressing to you that you can pull out scalars. And again, scalars work in the same way by multiplication. So it all really works the same. And again, linearity is of a very specific form. It has to be given as multiplication by an n by n matrix. Except now the entries of this matrix are complex numbers, not just real numbers. And again, these v1 through vn are all complex numbers. So it's all given of the same form, but everything goes through in exactly the same way. We've just replaced the word real with the word complex everywhere. And we so far haven't had a problem. And again, F is an isomorphism of complex vector spaces now, if and only if the matrix has non-zero determinant. So again, you compute the determinant. I should say in general, though, when you compute the determinants of these complex matrices, in general, you're adding and multiplying and subtracting things. Determinant will be in C. It will be a complex number that you get out of this whole process of computing the determinant of an n by n complex matrix. But 0 is a complex number, so as long as it's any number that isn't 0, any complex number that isn't 0, then this will be an isomorphism of complex vector spaces. So again, we can ask, well, what happens when n equals 1? Well, same as before. You have a complex 1 by 1 matrix, which means there's just one complex number sitting inside of it. And how does it handle being multiplied by a vector? And again, this is complex too. It's all 1 by 1. Again, it's just multiplication by that number. Alright, so GL1C is equal to the set of all, really it's all complex isomorphisms. Isomorphisms of complex vector spaces, where we're thinking of C as a one-dimensional complex vector space over itself. Or if you like, it's the 1 by 1 complex matrices. Right? So that squares with what I wrote here for GL1R. It's 1 by 1 non-singular real matrices. Sorry, I forgot about that. It's not 1 by 1 complex matrices, it's 1 by 1 non-singular ones. And again, the determinant of a 1 by 1 matrix, whether it be real, complex, or anything, is just the number itself. There's only one entry. So as long as I don't give you a complex number, a complex number which is 0, then we're good. We're in GL1C. So you can think of these as these sort of 1 by 1 non-zero complex matrices. And I want you to notice that, the only thing, listen, Z can be any element of the complex numbers except for 0. But I gave a name to that set earlier on in the video. I called it C cross. So really we can think of, if we go all the way back to the top, all the way through the linear algebra review and so on, all the way to the top here, C cross here was the set of non-zero complex numbers. We can put brackets around any such thing and think of it as, this is literally the same, except for these little 2 square brackets which are meaningless, as non-singular 1 by 1 complex matrices. So this is a very beautiful relationship here. We can think of these things as 1 by 1 complex matrices, and we can think of them as these 2 by 2 real matrices from the beginning, these matrices of the form A, negative B, B, A. So this is very intriguing. I'm pretty much finished with what I wanted to say, but let me just round things off for you and summarize what we've done so far. You can think of these 1 by 1 complex matrices as being 2 by 2 real matrices of a very specific form. Okay? These non-zero means that this is going to be non-zero determinant and everything else. So I called this map phi before. But the point is that both of these ways are great ways of thinking of GL1C, which is a group. And it also happens to be isomorphic to C cross, which is the set of non-zero complex numbers. So we have this nice kind of linear algebra, and what we're doing here is really nibbling at the heels of complex linear algebra, which, as we've seen, has been, pretty much the same as real linear algebra, although there are some differences, some more interesting things that happen in the complex case. But this is very important. I just want to show you matrices of this specific form can really, they can be thought of as a single 1 by 1 matrix of a complex number that just kind of gets expanded into a 2 by 2 real matrix. And if you had matrices that had more than one complex element in it, like an n by n matrix of complex number, then you can blow that up and expand it in, by doubling everything and just replacing each complex number by these little things, and it creates a relationship between GLNC, which is defined the way you might imagine it would be, and GL 2n r, because everything gets doubled and so on. I don't really want to explore this at all, but I just want to get your mind thinking in that direction. So matrices of this particular form are nice because of what? They're not just any old real matrices. They form a subgroup of the set of real 2 by 2 matrices. But what's so great about it is that they're in this one-to-one correspondence, this very natural isomorphism with 1 by 1 complex matrices that are non-singular. isomorphisms of complex vector spaces, things which respect not just linear algebra structure, vector space structure, but complex linear algebra structure. And that's really the point here. So we're going to see matrices of this form come up again and again with Cauchy-Riemann equations and so on, and we've already seen them before, and we've seen even that you can compute the norm of this z by the square of the norm by taking the determinant of this matrix. And that's really what I want to do. I want to show you that what we're really doing with these things is trying to preserve and respect the complex linear algebra that's sitting behind C, thinking of C as a one-dimensional complex vector space. So we'll see a lot more of that.